Hello and welcome to another finite element lecture. In this lecture, we are going to discuss another type of finite elements, which are called the solid elements. Actually, solid elements are one of the most widely used type of elements. At the end of this lecture, you will be able to identify nodes and degrees of freedom of solid elements, describe the concepts of parent elements and shape functions, explain the difference between linear and quadratic elements, identify the terms of the equilibrium equation of finite element models of solids, apply correct boundary conditions and forces, troubleshoot models with singular stiffness matrix error, troubleshoot models with the negative volume error, check and improve element quality, and identify symmetry in your models and use it to simplify the model. So why do I need to know about this? We know from solid mechanics theory that when a structure is subjected to external loads, stress and strain is produced inside the structure. There are experimental methods like photoelasticity that allows us to visualize strain and stress inside the structure. But the structure has to be made of certain material. For instance, here I've shown a protractor under loading, and you can see that with photoelasticity we can see the distribution of strain inside the protractor, and we can see strain is more concentrated at this corner. And perhaps from your own personal experience, you know that this structure usually breaks from this point. On the other hand, solid elements would allow us to computationally predict the distribution of stress and strain in solid structures made of almost any material. So, as I mentioned, solid elements allow us to determine the areas of stress concentration and improve the design of our structure if it is susceptible to failure, like this bicycle frame, where solid elements have allowed us to see the location of stress concentration here, and we can subsequently improve the design computationally. We use solid elements to discretize the medium. Here's an example. We have discretized the bone of this robotic gripper with tetrahedral solid elements as shown here. I mentioned tetrahedral solid elements. In reality, there are different types of solid elements based on their shape and number of nodes. 4 main element shapes are shown here, which are tetrahedral elements, pyramid elements, wedge elements, and hexahedral elements. And for each type, like tetrahedral elements, we have 2 variants. One with nodes that are located at the vertices, like this one, 4 nodes are located at the 4 vertices, and one which has additional nodes on the edges. You can see now here each edge has 1 additional node, and the same is true for the other 3 types of solid elements, where we have the version with nodes only on the vertices and the version that has additional nodes on the edges. A solid element is defined by the coordinate of the nodes and their connectivity. The connectivity means which nodes are connected together to each other. For instance, here node 1 is connected to nodes 5, 6, and 7, and so on. The degrees of freedom of a solid element in the context of mechanics are nodal translations in x, y, and z direction. For instance, here for this element that I have shown here, each node has 3 translations in x, y, and z, like u1, v1, and w1 for node 1. And this element, the whole element, has 3 times 10 10 equals 30 degrees of freedom. Here we have our tetrahedral element, the quadratic element, which has 10 nodes in the Cartesian coordinate system. And as you can see, this element, because it has mid-edge nodes, it can represent curvatures, curved geometries, as you can see represented by this element. This element is located in the Cartesian coordinate system, but there is a space that is parallel to this Cartesian coordinate system, which we call the natural coordinate system. In that coordinate system, everything is perfect. What do I mean by that? All the edges, these are straightened up, and the angles between the main axes, they are 90 degrees. This is the natural coordinate system, and this is the representation of our element in that coordinate system. We can map our element into the natural coordinate system, which is often shown by R, S, and T, and then we can work out the coordinates of every node, which are quite perfect. So what I mean is that, like node 1 in the RST coordinate system, which is the natural coordinate system, its coordinate is 0, 0, and 0. But if you look at node 2, which is now mapped into the natural coordinate system, the coordinate of that is 1, 0, and 0. And if you look at node 3, the coordinate of that is 0, 1, 0. And if we look at node 4, the coordinate of that is 0, 0, and 1. You see what I mean by having a perfect coordinate for these nodes in the natural coordinate system. So everything now is mapped into 1, and these angles are 90 degrees. And if we look at the mid-side nodes, again, similarly, we have quite a neat description of the coordinate of these nodes. Let's say node number 5. The coordinate of this is 0.500. And if we look at 6, for instance, it's 0, 0.50, 7, up here it's 0, 0, 0.5, 8 is there. So it's located on R and S. So again, the coordinate of 8 is half, 0, and so on. So this is how we can map our element from the Cartesian coordinate system into a natural coordinate system. And then you will see that the approximation of this element stiffness matrix is done in the natural coordinate system. It's much easier to do it that way. And then we map it back into the Cartesian coordinate system. The coordinates of every point inside an element can be determined by using the coordinates of the nodes and what we call the shape functions. You have seen the concept of shape function before in relation to beam elements. For a 4-node tetrahedral element, the coordinate of any point inside the element is described using 4 shape functions that I have shown here. These shape functions are described in the natural coordinate system. So you can see they have R, S, T as the variables. For instance, for node number 2 here, we know that R is 1 and S and T are 0. So just look at this. You will see that if R is 1 and these two are 0, N1 is 0, N2 is 1, N3 is 0, N4 is 0 as well. And if you insert this into these equations, you will see that it will work fine. So you will have the coordinate of node number 2, X, Y, and Z, and so on. These shape functions are linear. So you can see they are linear functions of R, S, and T. Hence, we say that a 4-node tetrahedral element is a linear element, meaning that its interpolation is linear. Now I have a question. If we know the translation components in X, Y, and Z direction, which are U, V, and W at each nodes of the element, how can we interpolate them inside or within the element? Well, an easy approach is to use the same shape functions that we have used here, like so. Then we call this element an isoparametric element because in this element, the element shape and the field quantity, which for us is the displacement field, are defined by the same interpolation function. Now let's look at a 10-node tetrahedral element. For this element we have 10 shape functions that are shown here, and these are quadratic functions of R, S, and T. We call this a quadratic element because its interpolation is quadratic. Again, for this element we use the same shape functions to interpolate the geometry and the field variable, which is translations in our solid mechanics problem. We can use matrix convention to write the displacement vector in terms of the shape functions and vector of nodal displacements. So let's look at this bar. This is like standard tensile test. We are applying a force that is pulling this specimen on opposite sides. You know, this is the type of experiments we do with instrument machines. We can zoom into one point within our domain and extract that infinitesimal element out of it. So if I extract an element, let's say from a region like this, that element in 3 dimensions is often shown with a cube. We call this an infinitesimal element. You shouldn't mix this with finite elements. So this is a mathematical definition of a point within our domain which has volume. So as I mentioned, this is a cube. And now we can look at different faces of this cube. So you know the force is applied in this direction. So if we use our coordinate system like X, Y, and Z, then force is applied on the Z direction. And you know if the cross-sectional area here is A, then here on this face of our element we have stress, a normal stress that is force divided by the area. And of course this element has to be in equilibrium because our structure is in equilibrium. Therefore on the opposite face, on the other side, on the bottom, we have the same amount of stress, which is F divided by A. So I'm sure you're familiar with the concept of normal stress this way. Now if you look at this experiment, this is a standard shear test where you see that these forces are shearing our rod. So again, if I zoom into this region and take an infinitesimal element out of that region, then that element, again, we represent it with an infinitesimal cube like this one. Right? And here we have a force that is applied downwards. So on this face of our element, we will have a stress that is a shear stress. So that stress is within the face here, and it is parallel now to the z-axis. Okay, so if we take that one, so this stress will be like this because our force is working downwards, and the amount of this stress is force divided by the cross-sectional area, right? So if we call this cross-sectional area A, but you know that our element, our structure is in static equilibrium Therefore, we have to have another stress or another force on this face on the bottom that is passing through this edge. Therefore, the moments are zero when we look at the free body diagram. So that one, I can show it with that. So this is as well tau, which is F over A. So this is the shear stress applied here. But you know that this element is not moving in Z, in Y, or in X direction. So in X, we don't have any forces. But in Z and Y, we now have this force or this stress and this stress. Therefore, there have to be other stresses that are balancing these two. So one has to be this way and another on this face should be working upwards. So these two cancel each other and these two cancel each other. So this way you can see the definition of the normal stress and shear stress by using this infinitesimal element. So now let's look at our infinitesimal element under the most generic loading condition. So we can have normal stress on each face. So in X direction, on this face we have sigma X. On this face we would have sigma Y. So this is normal stress due to the force in Y direction. And here we can have sigma Z. And then we have shear stresses as well applied on all these faces. So on this face, which is an X face, we can have a shear stress that is aligned with the Y-axis. So we call this tau xy. And as you remember, if we have this one, we have to have another shear stress on this face that will balance this one. So that's tau yx, which is equal to xy. So again, I use tau xy here, which is equals to tau yx. And on this face, you can also have a shear stress that is along the z-axis. So it will look like this. And this one, we can call this one tau xz. And then we should have another one on this face, which is equal to this one and pointing to the same edge. So that would be tau xz, which is equal to tau zx, right? So this is a z face and stress in x direction. So that's tau zx, but we know due to equilibrium, these two are equal, tau xz and tau zx. As well as this face, if you look at that one, so that is a y face. So here you can have tau yz, and here you can have tau yz, which is equal to tau zy. Yeah. And of course, I'm not showing the stresses on the other faces that are hidden. So on the back, bottom, and on the other side, we have stresses that are balancing the ones that you saw on these three faces, but I'm not showing those ones. So essentially, here in this generic case, you have 6 independent components of stress. So all put together, you have 9 components of stress, and only 6 of them are independent due to equilibrium. This is called a tensor. Stress is a tensor. So tensors, they follow certain rules for transformation. Scalar is a tensor, but this is scalar is a 0th order tensor, like temperature. Okay. Vectors are first order tensors. Examples of vectors are like velocity or acceleration or displacement vectors, and they have certain rules for transformation. Stress is a second order tensor. We are going to see another second order tensor, which is called the strain tensor. We can write the components of the stress tensor in a matrix like this. In this matrix, the diagonal terms are the normal stresses, and the non-diagonal, they are shear. So here we have xy, here we have tau xz, yeah, and here we have tau xy again. So this is tau yx, which is equal to xy, and then diagonal term is sigma y, and here we have tau yz. And then moving to this one, this is tau zx, which is equal to tau xz. This is tau zy, which is equal to tau yz. And again, the diagonal term here is the other normal stress, which is sigma z. This is in matrix format, but we can also write it in a vector format. We can write this matrix in a vector format. You know, in this matrix, we have only 6 independent components, so that vector has only 6 members. That is called the void notation, which would look like this. So you can imagine here, we will have all the normal components. So sigma x, sigma y, and sigma z, and then we will have the shear components. So tau xy, tau yz, and finally tau xz. As I mentioned, strain is also a second order tensor, which we can write it in with a similar format. So in a matrix format, strain can be written like this. So you can have normal strain, which we often show with epsilon. So we can have epsilon x. This is the normal on the diagonal region. We write these ones. And then we also have the shear, right? We have the shear strains. So here we have gamma xy divided by 2, and here we have gamma xz divided by 2. And then similarly here you have gamma yx, which is equal to gamma xy divided by 2. We have epsilon y, and here we have gamma yz divided by 2. And then here we have gamma xz or zx, they're equal to each other, divided by 2. Gamma zy or yz, they're again equal to each other, divided by 2. And then finally the other normal strain, which is epsilon z. You may have noticed that here I'm dividing gamma by a factor of 2. You need to do that in order to have a tensor, so that this tensor can follow those transformation rules. But when we write this in the void format, the vector format, we avoid that division by 2 of the shear component. So here we have epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, and gamma xz. So you see, we have corresponding vector of strains, and here we have vector of stresses. So here we have the vector of stresses, 6 independent components, and vector of strains, 6 independent components. You know that we can link these two with each other by using the material model or the constitutive model. So the simplest model that we know of is the linear isotropic, where by using Young's modulus and Poisson's ratio, we can link stress and strain. But the material can be more complicated, like composites, orthotropic, or other responses like nonlinear. So in general, we write that function like a matrix E, which is our constitutive equation, okay? Or we can write this as the vector of stresses equals our constitutive model times our vector of strains. Okay, so that is how we would link our stress with our strain. But what else we know from solid mechanics is that our strain can be determined by using the displacement field. So you know, displacement field in structural mechanics refers to displacement of every point within our medium in x, y, and z direction, which often we show with u, v, and w. So the way actually they are linked is that epsilon x is du dx. So that's the derivative of displacement in x direction by x. Similarly, epsilon y is dv dy, and you can imagine epsilon z is dw dz. Okay, and similarly for these shear strains, we can use derivatives to find them. I'm not going to write all of this, but I'm going to write everything in a matrix format. So if we have the vector of strains like this, so that would be epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, and gamma xz, right? So I'm going to write this in a matrix format. So here I have a matrix that includes all the derivatives that I just mentioned, and then I have another vector here, which is the vector of displacement, so u, v, and w, so displacement of every point in x, y, and z direction. So you can imagine here on the diagonal term, here we will have d, dx, and 0, 0, right? So if you multiply that by this, it just gives you du dx equals epsilon x, and then this one would be d dy, and this is 0, and then this is 0, 0, d dz. Okay, now when it comes to the shear strains, this will be d for the first one, so just make sure I'm doing it right. So this will be d dy, d dx, and 0. So this will be du dy plus dv dx, and this one is 0. So that gives you gamma xy. Next one, yz, this is 0, and this is d dz, and this is d dy. Okay, so that would be dv dz plus dw dy. And the last one, so I need to extend this a little bit further down here just to accommodate the last one. That one is d dz 0 d dx. Or neatly, we can write it as vector of strains equals this matrix, which is the matrix of derivatives times the vector of displacements. Right, now we are going to use what we've learned so far based on isoparametric elements, based on recap of solid mechanics, in order to estimate strain within an element as a function of displacement at the nodes. How do we do that? So first of all, from solid mechanics, we now know that strain, so let's call it strain tensor, we show it like a vector notation, is d, right, u, which is displacement. Okay, so this is vector of translations, and this is strain tensor. I know this is a matrix that shows the derivations. So we have that equation. We also know for isoparametric elements, the translation or displacement field, so we show it with a curly bracket like this, can be determined by using vector of nodal displacements and the shape function, which we show with n. So this is the tensor that includes all the shape functions, and here we have vector of nodal displacements. Okay, so you can see where I'm going with this. So now we can replace this u, this vector here. Here this is supposed to be d. So this is the vector of nodal displacement, which we always show with d, right? So now we replace u with this bit, and let's see where we go with that. So we will have then epsilon equals, there will be this matrix that includes all the derivatives, and then we have n. So this is a matrix that includes all our shape functions, and here we have the vector of nodal displacements. Okay, well, it sounds good. So it seems that now we can find the strain from the vector of nodal displacements, but there is a problem here. If you remember, all these derivatives that go into this matrix, they were with respect to x, y, and z. Hence, they were in the Cartesian coordinate system, right? But our shape functions, they are in the natural coordinate system. So let me highlight it here. So these ones are functions of x, y, and z. And these ones are with respect to r, s, and t. So they are in two different coordinate systems. So we cannot directly apply these derivatives to n's. We have to do something. We need to use the so-called, well, you know about that. So when we do differentiation, we can use the chain rule. So we can now change from one coordinate system to the other by using the chain rule. So what I should also mention here is that we can also simplify this further to write it as a B matrix times vector of nodal displacement. So essentially, our aim now is to find this B matrix by using the chain rule. So here you can see that I'm using the chain rule here just to replace the derivative of the shape functions with this equation. And here I have the inverse of a matrix, which is a derivative of the positions in the Cartesian coordinate system with respect to the axis in the natural coordinate system. And I know that position or coordinate of any point inside the element can be described by using shape functions like this. And now things are simple. Why? Because n is a function of r, s, and t, and these derivatives are with respect to r, s, and t. So essentially we can do these derivatives. And xi, yi, and zi, these are known coordinates of the nodes of our element. So we can replace, we can name this matrix J. J is called the Jacobian matrix, and its determinant is called the Jacobian. Well, it's not only a mathematical definition, it has physical meaning. For linear elements, J or Jacobian matrix is constant, and its determinant is 6 times the volume of the tetrahedral element that I have shown here. However, for quadratic elements, J is not constant anymore, and it will be a function of r, s, and t coordinates in the natural coordinate system. Okay, I have skipped a few steps here. So I've not shown really how we have come up with this integral, but you know the terms inside this integral. So essentially this integral includes the B matrix I introduced before and the constitutive model. And this is an integral over the volume of the entire element. And what it gives us is the element stiffness matrix. So for linear elements, we showed that the Jacobian matrix is constant and hence B is constant, and this integral then can be evaluated analytically. Of course, if our material is linear elastic. For quadratic elements, B is a function of R, S, and T, and the integral should be evaluated numerically. One of the methods that is widely used to evaluate this integral numerically is called the Gauss quadrature integration scheme, which is like this. So if you have a scalar that you want to find its integral over certain volume, you can break it down into sums, and you can essentially sample this scalar at different points within the volume. So I have shown 4 points here, and these are called the Gauss points. And once you sample here, then you can multiply it by Ji. This is the Jacobian evaluated at that point within the volume, and this is a weighting which is well defined for the Gauss scheme. So if you want, we can look at the Gauss scheme and you will see the weighting for different number of integration points. Okay, now that we know how the element stiffness matrix is formulated, then we can formulate the equilibrium equation, which looks like this for a solid element, where we have the element stiffness matrix times the vector of nodal displacements or translations for solid elements, and these are equal to the vector of nodal forces, or I can write it in an abbreviated form like this. So here I have shown this equation for a linear tetrahedral elements, and you can see for a linear tetrahedral elements we have 12 degrees of freedom, and therefore this is the size of this vector, size of this vector, and size of the element stiffness matrix 12 by 12. For the quadratic tetrahedral elements, however, the size is larger, so we have 30 degrees of freedom, and this is the size of different vectors and matrices here. But essentially what the take-home message here is that the equation you see here, the equilibrium equation for the solid element, is exactly the same as what you have seen for truss elements and for beam elements. The only difference is that the components, the members of these matrices are different, and the size of the matrices are different. So how about the structure described with solid elements? Here I have shown a model made of two solid elements. The equilibrium equation is as what we have seen before for beam and truss FE models. The vector of nodal displacements contains translations at nodes, and the vector of nodal forces contains the external forces applied to the nodes. Well, so far we have seen a bunch of theory, but how do we solve problems? No worries, software will do it for us, but we should define what the software needs to solve the problem. And what we need to give to the software when we're using solid elements are nodal coordinates, so coordinates of the nodes, which is generated when we do the meshing, as well as connectivity between elements, and material properties. For instance, if you use a linear elastic material, these are elastic modulus and Poisson's ratio. So all together, these will define the structure stiffness matrix. Then we need to define boundary conditions. So these are known degrees of freedom. And finally, we need to define the known external forces, which will go to the vector of nodal forces. Here is a problem that can be solved by using solid elements. I have solved this problem in a supplementary video, which I encourage you to watch it first before continuing. You will see how the theory that we have described so far can help us to set up the FE model and understand the available options within the package. Okay. I'm showing the same slide that I showed before in relation to beam elements and trusses. If you recall from those lectures, we can rearrange the equilibrium equation of the FE model in terms of known and unknown values like this. And we can solve for dx, which is the vector of unknown nodal displacements, like so. And then we can find the unknown external forces. Again, we should note that in order to solve this problem, we need to find the inverse of this matrix. So we should make sure that this matrix is not singular. So what can make the stiffness matrix singular? Yes, inadequate support. For instance, in our problem, if we fix only two nodes as shown here, this node and that node, you will see that the software will return an error. This is because this structure, the bone, can rotate about the axis that passes through these two nodes. Hence, this structure will not be in static equilibrium. We can use symmetry to simplify finite element models. In order to do so, the geometry, material, boundary conditions, and loads must be symmetrical with respect to the plane of symmetry, okay? So you should always make sure that all four of these are symmetrical with respect to that plane. For instance, a plane passing halfway through the thickness of this bone satisfies these four conditions. Hence, we can remove half of the bone, as you can see here, and apply appropriate boundary conditions on the cross section which is exposed now. And the boundary conditions is that we make the translation in y direction 0. The predictions of the full model and the reduced model should be the same, and I really encourage you to give it a go. One limitation of the finite element method is the discretization error, but do not worry, we can control it. One thing that we should always do is to check the quality of our elements. One metric that is used to check the quality of elements is called the aspect ratio. Aspect ratio is related to the ratio between dimensions of the element. So here I have shown an ideal element. So this is the parent element, the element that has these edges equal to 1 in the natural coordinate system. This element is ideal because this gives us the best approximation when we do the estimation to find the element stiffness matrix. Any deviation from this ideal element means that we are getting away from the ideal solution. So here I have shown an element with high aspect ratio. The rule of thumb is that the aspect ratio should be less than 3 for the majority of the elements, and more importantly for elements that are located in areas of concern, for instance areas of stress concentration. So now you know that if you receive errors or warnings about the aspect ratio, these are related to element edges being placed on a small feature in the model, for instance small edge. In some packages you are able to even remove those edges or link edges so that you are not forcing the software to put a small edge or small element on that edge. Another mesh quality metric is called the Jacobian ratio. And now hopefully you will appreciate why I spent a few slides to explain what is the Jacobian matrix and Jacobian. Jacobian ratio is a measure of the distortion of quadratic elements. So essentially it is related to the placement of mid-side nodes on the actual geometry. So just look at this geometry. So the mid-side points are located here, there, and there. But if this was more skewed, so if I had a much sharper edge here, this node would have been more inclined towards the center of the element, and therefore I would have had a much more bent edge of the element. And this means more distortion in the element and higher Jacobian ratio. For an ideal element, the Jacobian ratio is 1. So an element which has straight edges, it has a Jacobian ratio of 1. This is an element that has a Jacobian ratio larger than 1 because the edges are curved. The rule of thumb is that the Jacobian ratio should be less than 40. Too much distortion of the element can cause actual problems when the software is solving the problem. It can lead to the error that is called the negative volume error, and this is when two edges of the element are crossing each other. For this situation, the Jacobian will be negative, which is not physical, and the software will crash. So if you receive errors or warnings about the Jacobian or Jacobian ratio, you know that they are related to mesh distortion on extremely sharp or curved boundaries. Okay, we covered a lot in this lecture. So in summary, we learned about nodes and degrees of freedom of solid elements, which are translations x, y, and z directions. Linear elements and quadratic elements were introduced. We learned about numerical integration to determine the stiffness matrix of quadratic elements. We learned about the structure stiffness matrix, vectors of nodal degrees of freedom and nodal loads or forces, the singular stiffness matrix error, which is usually related to inadequate support, checking the mesh quality by using the aspect ratio as well as the Jacobian ratio. And finally, we learned how to use symmetry in order to simplify FE models. Thank you for your attention.